Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, and thanks very much for the invitation to come and speak here. So I'm actually from the CNRS, permanent researcher based in the Sophia Antipolis in the south of France. And I'll try and make a bit more of an effort to integrate into the different aspects of the other sessions. Basically, I think there's a lot of overlap. So in this talk, I will speak a little bit about 3D modeling, and I think there's a lot of overlap with the computer graphics community, but I'd like to try and look at that from a robotics perspective and try and rethink some of that. I think a lot of work has gone towards inversing the computer graphics pipeline for computer vision without rethinking it for our particular applications. And in terms of interaction, I think that what I'm going to show is more sensors that are going to be moving up into the environment. So we're no longer looking at a static sensor that's just observing someone interacting with a computer, but it's actually the computer that's going to be out interacting with the world. So a lot of this work has been done in collaboration with several students and also a researcher from INRIA in Sophia Antipolis, Patrick Reeves. So basically, a lot of my research since around 2005 has been looking at this kind of core problem for a lot of robotics applications, in that we want to know where the robot is positioned in space. And to be able to know where it's positioned as it's moving through space, we need to also have a map. So this is this chicken and egg problem that we need to solve simultaneously. And we want to be able to do that in large-scale environments with very complex scene geometry, so we can't easily start applying lots of different types of features, planar objects, lines, etc. But we want to be able to just have some sort of general representation. And importantly for robotics is being able to do all that in real time. So our solution has been to go towards more image-based approaches or sensor-based approaches. So we want to stay as close as possible to the sensor information so that we can compare that with the online sensors of the robot. So this kind of deviates from these 3D graphics models where we have texture mapped 3D models with aliasing effects and trying to cater for all different viewpoints. Rather, we're going to start looking at maps that are dependent upon the trajectory or a given set of trajectories that the robot can undertake to navigate through that environment. And we're going to deviate also a little bit from a lot of thrust in the computer vision community towards feature-based approaches. So we strongly believe in these sensor-based approaches. So we call that direct approach, where we minimize directly the sensor information or the image intensities. And we've found that to be very robust statistically and very precise. And it allows us to avoid all these feature extraction errors and feature matching errors, because we don't have to do that anymore. And we're actually getting feedback from the global information towards this kind of low-level stages of the processing. And I'll try and show a little bit how we treat the different criticisms of these direct approaches by looking at how we can model dynamic changes in the environment, such as illumination changes, and how we can develop a generic model for any type of sensor. So just to give a first kind of overview, maybe a little bit technique, but the rest of the approach is kind of based on this. So back in 2007, we first published some work on dense localization and mapping. So basically we have a set of photometric color images. We have potentially depth images. So we also, we didn't have access to the prime sense sensor in advance like Dieter, but we were already working on stereo systems. So we can we can consider a stereo system to be RGBD system. And so we have this novel view synthesis, which you probably, most of the people in the vision community are well aware of. And we like to warp a current image using knowledge about the pose, so 6 degrees of freedom pose, and the depth of the points, so that we can warp that to a reference image. So instead of having a 3D model, we're basing everything with respect to the sensor information, and most of the time we'll just take the first image to be the world reference frame. So we have just the incremental estimate, so we're looking at nonlinear iterative estimation incrementally. So we're most of the time looking at very small increments between 2 time instants at 45 frames per second. So we can assume that there's very little movement between the different images. And we build up a global representation of that by optimizing a robust optimization criteria. And by defining this robust optimization criteria with respect to all the information in the image and not just certain features or patches, we can get some nice robust statistical properties through an M estimator. So this is basically the stereo configuration. We had a look at modeling that through the quadrifocal geometry between a reference stereo pair and the current stereo pair. So we have a whole set of relations that allow us to describe the transformations between all the images. And we found that the base relations that were the most important was going from the left reference image to the left current image through a trifocal tensor. So the quadrifocal decomposes into trifocal, and we end up with 2 trifocal tensors that will transform left and right images onto one another. And so basically we're defining a plane in the right image through a corresponding point. So this is, for the stereo case, we have correspondences spatially for dense matching, but we don't have correspondences temporally. And we don't keep the features, so we will be considering directly the intensities. So this is just basically a geometric warping function for the stereo pair, which depends on a certain set of underknown pose parameters. And this is just some of the videos that we were doing back then. So here we have very accurate visual odometry in 6 degrees of freedom. You can see the stereo pair being used for the estimated 6 degrees of freedom odometry. And we can see that we're able to do a full tour of around 200 meters with only around 2 meters drift at the crossing point. And we have mobile objects, we have flickering lights, which are all able to be successfully handled by the M estimator. So we can see here just a little bit of information on the M estimator. So we can see down the bottom the different parts that are being rejected from the data. So we can see that there are some parts of the scene that aren't visible from left to right cameras. We have moving cars. And we can see that the images jump every now and again. So this is when we're changing reference image periodically based on robust statistic criterion that will detect when the robust variance gets too strong. So we kind of, with the arrival of the Kinect, went on to looking at applying these techniques to the Kinect. So I guess you're all aware of the geometry of the Kinect. So I'll just move on to this kind of base optimization, which we call direct iterative closest point, because we still want to maintain this direct minimization criteria based on the raw sensor data. But in a lot of these devices, we're only able to obtain the raw depth also. So we can start to consider these sensors as providing both intensity image and depth image. So we minimize directly the raw intensities warped from the current image to the reference with the reference image, and also do the same with the depth image. We have a warping function for this depth image. And then we have this scale factor that allows us to take into account the relative uncertainty in the two sensors. So we had different sets of choices for the depth warping function because we have all these inverse compositional or forward compositional approaches which allow us to pre-compute different parts of the estimation problem beforehand and make the estimation more real time. So in this case, we're able to reuse some of the data or some of the computation that was made for the intensities by doing a forward compositional approach. And so we end up with an estimate of the poses, and as I'll show later, also the depth. So this is just a picture of this closed loop nonlinear estimation process. And so we can see that we're actually closing the loop, the error on the sensor data. So we're not introducing any open loop error on the features or on the feature matching process. And so with this, we've kind of saw that we got some really good results using the whole image, using robust statistics on that, and we wanted to push that further. So we started looking at having a sensor-based approach, which was even more dense. We wanted to have full spherical panoramas, but we need this depth image. So we started working on building this kind of ego-centered representation, which is a set of spheres, kind of like what we'll find on Google Street View, but with dense depth images on the spheres, and using that to perform navigation and localization. So each sphere is composed of the photometric component and the depth image, and we also have a saliency map, which tells us which pixels are more interesting to constrain the full global problem. So basically the classic sensors that we have to be able to do this all try to aim at having a common central center of projection. So we went out and expressly built a system with baselines between all the cameras. So this was our first system. We had quite a lot of difficulty because we have diverging angles of the cameras, and when we try and warp all the difference of the 6 cameras around the ring onto a central sphere, there where we're missing depth, we couldn't warp the photometric information onto the sphere. So recently we have developed a new system that has just a single baseline, and basically it's a set of 3 stereo pairs back to back looking outwards, which gives a lot better information. So this is just a video of the output of this sensor. So we can see we're obtaining nice 180-degree panorama, and we have quite dense depth information on the bottom. So once we have these sort of dense sequences in the environment, we can start to look at using that for navigation. First, I'll just talk a little bit about how we position the spheres in the environment. So basically, we have this direct estimation approach for the entire sphere. So we just minimize directly the intensities and estimate the poses between the different spheres. And we'd just like to determine where we need another sphere. So we do that by looking at the median absolute deviation of the error distribution. And if we detect that that's getting too large, then we place a new sphere. So yeah, for the moment, we've just looked at this kind of very efficient criteria, but I think we have some more work to do to work out how to optimally place these spheres in the environment with respect to occlusion boundaries and things like that that are not handled by a sensor-based approach, that are handled by classic 3D model-based approaches. But we have the advantage that for our applications, we have this photorealistic rendering of the environment. So this is just a video of this representation. So we've got the spheres in red. We're just choosing the closest sphere and to the current camera position, and we can generate novel viewpoints locally around this trajectory, which is sufficient for navigation applications. We can see if we come out of the graph, we lose a lot of the precision, but we only need that locally around the trajectory. And so we can start to see a lot of applications for gaming or robotics or augmented reality. And because we have this sort of compact representation, kind of Google Street View style, we can start to look at also having compact packets that can be transferred onto mobile devices for navigation purposes as well. So I talked a little bit before about how to handle dynamic changes within the environment. So often we'll have an expert system such as this that will go and map the environment for us. And we'd like to use a low-cost sensor online to go and navigate and localize ourselves with respect to that model. But often, if we're outside, we have a lot of illumination change from morning to night or through the seasons. So basically, we talk about model-based approach in the case where we're localizing with respect to this previous model. So we have all the depth maps, we have the full environment reconstructed and referenced with respect to a world reference frame. But the problem here is we can have very, very large changes with respect to the current online sensor. But we also have the visual odometry approach, which just computes these parameters incrementally over 2 time instances. And there we can have very little change between 2 images at 45 frames per second. So we just simply combine these 2 approaches. So what we do is we simultaneously estimate an error with respect to the model and respect to the visual odometry. And we can also take leverage of the depth maps computed for the model, for the visual odometry part, because we know that that's correct. And we just introduce the intensity component of the visual odometry into the system, so it still stays very efficient in terms of real-time estimation. So this is just a picture of the dual estimation process. It's probably more interesting if I show you the video. So here we have quite a few different scenarios that we have tracked. So this is our tracking system. We have the reference image in the middle at the top and the associated depth map. We have the current image that we want to register with the reference one. So this is just, the first part here is just one increment. So we've purposely introduced a large displacement between the 2 cameras, even though in typical situation we are much closer. We can see that there is quite a large domain of convergence. We can see the robust weights and error on the left. So we can see at the end of the minimization, because we have very large illumination changes, we still have residual error with respect to the model-based approach. So that actually gives us a dense illumination map, pixel by pixel, with the change with respect to the model. So this is the online tracking system. Here we're building up a model of the environment, so we can see the different reference images or spheres presented in blue. And we have the 6 degrees of freedom relationship between the cameras. And then we do this tracking in real time, so we're just selecting the closest reference image in red and performing minimization with this saturations. So there's actually a bay window just behind the camera, so there's a lot of daylight coming in, even though it's an indoor situation. And so we tested global illumination change, where we have gradients inversed in the image. And we also have tried local spot changes on local parts of the scene. So we can see that we're getting close to millimeter accuracy with the stereo system. We also tested changing the calibration parameters on the camera, because we are quite robust. We have this closed loop estimation process, so we can defocus, we can change the aperture size, which changes a lot of the illumination in the scene. And we can see that the camera pretty much stays still in the aperture change, but when we actually change the focus of the camera, we can see we're just playing with the depth, the Z estimate of the pose. So it's just giving the precision. But with a lot of the applications for robotic navigation, it doesn't matter too much if we are not metrically accurate globally, as long as we have some sort of closed loop estimation locally that maintains a correct estimate. So this just keeps on going on with different types of illumination change. So this is some of our work on the Kinect sensor for doing direct ICP. So it's quite similar to the work with Microsoft and Imperial College on doing the Kinect fusion. But here we're using our egocentric approach, so we can see the raw image here being integrated over time. So we're not actually creating a volume as they do, but we're just keeping these reference images and then propagating the integration over time. And we can see that we're able to maintain a quite high resolution estimate of the depth and the intensity maps of the scene. On the top left is the normal of the different surfaces, so we can actually get a lot of very interesting information out of this. And I have just another small video here with the Kinect. So once again, using these direct approaches, minimizing both intensity and depth. So we can see we've got some problems here with automatic gain on the sensor. We don't have access to a lot of the internal workings. So we have to put up with these intensity changes or do blending techniques to deal with that. So quite similar to some of the work by Dieter Fox also. So here is just our virtual navigation through these environments. So this large scale here has only median filtering on the depth parameters to be able to get to filter the scene. So I don't know if I have time. I've just got a small video here of autonomous navigation. So this is basically we have an outdoor situation here. We're in the center of town in Clermont-Ferrand on an electric vehicle, and we're using this egocentric representation to teach the robot a given trajectory that we'd like it to follow. So this is the learning phase. We just drive around manually and gradually build up the model. So we really had a lot of problems with the illumination from morning to night. We also had we also saw that our saliency selection criteria that actually looks at not only the gradient within the image, but looks at the full Jacobian of the warping function to select the most interesting information, was able to work quite well, because we had a lot of points along the square at infinity, which would have been selected by kind of classic Harris type gradient in the image detectors, and we would have lost all the information that would have constrained the translational component. So this is just building up the model. Just kind of skip along. So we had 1 kilometer round trip around the square in fully natural environments, and then we use this in an asymmetric kind of configuration. So we have this this model that's been built up, and then we just used a monocular camera to localize the robot with respect to that and to determine its trajectory. And so this is just a video of the autonomous navigation. So you can see that we also have a laser sensor, but all of these approaches are uniquely vision. We're not introducing any inertial information or anything else into the estimation process. And the laser is just there for security purposes, so if someone walks in front of the vehicle, it will stop the vehicle. And so it's able to handle all these largely dynamic changes in the environment with pedestrians, trams, changes in illumination, etc. And so it doesn't matter too much that with the actual global model, we actually had quite a fair bit of drift with respect to the... Okay, we learned the path through the gate, so we forgot to open. But yeah, so it doesn't actually matter that the global model isn't metrically precise, as long as the local part of the minimization maintains the same image warping. So we can actually have this metric topological representation that allows us to navigate even with non-metric global models. And so that kind of concludes my presentation. So maybe it has some ideas for thought to rethink this kind of computer graphics pipeline. I spoke with a few of the graphics people earlier, and I think they're still even looking into these type of image-based approaches also. And also for doing localization and mapping, I think that even maybe with these kind of direct, dense approaches, it's maybe possible to work towards higher level information. So trying to use these direct approaches for semantic, higher level scene knowledge. Maybe there's a way to rethink that so that we don't have these huge feature descriptors, but we maintain somewhere in the representation this direct, raw information that allows us to have keep the touch with the world and the real sensor information. So.
That's great. Thank you, Andrew. And Andrew,